Over to here, sign into Canvas. But I gotta type it in again. Okay. Entering verification codes. Okay. All right. How are y'all doing today? Like that. Okay. All right. Let's pull up where we're at. Okay. So we've been talking about alcohols and how we categorize them as primary, secondary, and tertiary. So here are our objectives. Huh? Boiling points? Okay. All right. Let's pull up the notes really quick. I'm just going to kind of pick through them. Download it. All right. Trying again. Okay. Oxides. We did the IUPAC names. Hydrogen bonding and alcohols. Ethanol. Okay. All right. Let's go ahead and look at preparation of alcohols and ethers. All righty. So I'm going to make this a little bit bigger. Okay. So we've got alcohols and ethers. Remember, alcohol has the OH and ethers do not have that OH on there. They're an oxygen connected to two different R groups. So SN2, what does that mean? Y'all remember SN1 and SN2? Stupid nucleophilic reactions, right? Substitution, right? SN2. Substitution, nucleophilic reaction, and it's bimolecular. Okay, so customarily when we're making ethers and alcohols, we do it by this method. So this makes ethers and makes alcohols. Now, if we remember, ether looks like this, and an alcohol looks like this, right? So when we're dealing with substitution types of reactions, we're swapping something out. So the example we have up here, what are our things that, let's look at it this way. What do these two molecules have in common? right here. What do these two things have in common? Well, right here we do. I'm talking about these two. So they're both alkanes, right? They're both alkanes. What else do they have in common? Go ahead, it's all right. What else do they have in common? They're all single bonds. Do these two things have anything in common? Well, they're halogens. Yes. So, most of the time when we're looking at substitution reactions with alcohols, for our SN2 reactions, we look at them having halogens. So, why would a halogen be a good idea if you're trying to do a substitution reaction? They can be reactive. Yay! It's okay. Sorry. Okay. All right. So both of these will take all of the electrons in that bond, right? Both of these will take all of the electrons in that bond. So this bromine is going to take both of these electrons. And since it does that, it pulls on these electrons. So it's more electronegative. What does that do to these carbons here? It does what? Y'all have it. You gotta get over your imposter syndrome. Huh? So it makes the bromine more negative. So if I have something between a carbon, right. So if the electrons are moving this way, this is where our electrons are moving. It's going to give us a slightly negative charge here and a slightly positive charge here, right? Now, which one of these is attracted to positive charges? Bromine. Since it's attracted to positive charges, this is our nucleophile, right? Phile means loving, right? So if it loves positive charges, it's going to be a nucleophile. Why does it like positive charges? Because it's got that partial negative, right? So when we're dealing with a nucleophilic substitution, we're swapping out nucleophiles, right? So this is our nucleophile. So in this case, we've got an alcohol coming along. There's all these electrons on here, right? They're sharing a pair right here. So this has a full negative charge. So it's also a nucleophile. So since this has a full negative charge, which one of these is it going to be attracted to? The carbon. So these two are going to become attracted to one another. So this little negative charge here comes from these electrons. It's going to be attracted to this carbon. And when we're dealing with a nucleophilic substitution, we're swapping out one nucleophile for another. And that's how we end up with that alcohol. Well, remember the difference between ethers and alcohols is that in alcohol, you've got the hydrogen that's attached to that oxygen. Well, with an ether, you're going to have a carbon attached to that hydrogen, attached to that oxygen, not a hydrogen. So we can have the same type of setup with this, But if we're doing it with an ether, and have another halogen, I'll use it the same way with bromine. We'll pretend it's bromine, right? Electrons are moving this way, so that's slightly negative, slightly positive. Now, if I have this going on, is that OCH3? I think I have too many electrons on here. Actually, that's not too many. That's right. Okay. So I've got a negative charge here. Yep. Got its extra set. So the same thing's going to happen here. This carbon, since it's slightly positive, is going to attract this oxygen. So this one kicks off as this one connects. Oh no, I just used the same one there as I wrote on the board. It doesn't matter if it's chlorine or bromine. Yes, I thought I would keep it to the same halogen, so if you wrote these side by side, you would see the main difference is what we're adding to it. If this was a chlorine, it'd pop right off. Bromine pops right off. You can just pick any flavor of halogen almost. Iodine, bromine, chlorine. Fluorine doesn't work so great. But these three right here. Yes, that's right. Because while this bromine is super electronegative and this chlorine is, which one of these carbons are going to feel the effect the most? The one connected to it, right? That carbon is going to feel the effect of this halogen taking everything more so than any other carbon. So this comes over here and kicks off this bromine. And that's how we end up making an ether. All right, so we have a name for that. Williamson ether synthesis. So Williamson, I assume, is the person who came up with this. Usually, if it sounds like a last name, then that's the person who did it, right? So Williamson ether synthesis. Unsymmetrical ethers can be synthesized in two different ways. One path is usually preferred. So when we're talking about, here we've got a word here, alkoxide attack. Alkoxide. Let's break down what it means though. You guys have been working on prefixes and suffixes and all that stuff for a while now. So when we see a new word like this, okay. Yep, so we got an oxygen involved. And then we've got some kind of alkane, probably alkane. If you see that ALK, you can think alkane, alkene, or alkyne. So you know carbon's going to be involved. So here we've got our nucleophile in this case. This is our alkoxide, right? And here's another alkoxide. We'll just say it's that for now. So we've got carbon chain. I for real just sat up here, wrote CHANE. For chain. Alkane, chain, it rhymes. Must be spelt the same in my brain, right? So carbon chain, oxygen, usually ion, negative charged. Alkoxide. You think of sodium chloride, IDE. If it's that IDE, that means it's in its ionic form. Okay. So if we're wanting to make an ether, we can use different forms of alkoxide. You see here in this one, this oxygen is attached to a carbon that's attached to just one other carbon, right? So the structure is different. This one is attached to a carbon that's attached to two other carbons. So in this case, this would be like a secondary alkoxide, right? This is a primary alkoxide because that carbon it's attached to is attached to one other carbon, one primary. This one attached to two, secondary. Okay. So let's talk about what's going on with these arrows. I started to draw them a little bit here and a little bit there because I know we get some confusion about the arrows. In a molecule, what particles are the things that move within a molecule? What are the things that cause bonding to happen? Is it protons? What is it? Electrons. Y'all know more than you think, man, for real. Y'all thinking, yeah, that's right. I knew that. Come on now. Electrons are the things that move. So these arrows, even when I draw them with our polar molecules, that means these electrons are moving towards this bromine. Now for this one, the electrons are moving towards the carbon. Why? Because that carbon's slightly positively charged. Well, this is with an alcohol. But here, yeah, when we're looking at these little arrows, these electrons are going like, hey, this carbon's slightly positive. So it's attracted, these electrons are attracted to that carbon. And what's going on with this bromine, once carbon starts to hook up here, let me just draw it. I'm going to draw it over here. When carbon starts to hook up with those other electrons on that alkoxide, it kicks, bromine will take the rest of those. So let's look at that first one over there. So I'm going to draw, I'm going to use colors. I find colors help. There's my black marker. Okay. So we're going to show the movement of these electrons. All right. So if we've got something like this, let's see, I'm just going to write what's on the board. We got this here, negatively charged, right? And then we've got the 2-bromopropane. Okay. And then we've got okay. And it's like this. All right. Is that up on the top? Yeah, they got it written that way. Okay. So I already know that between this carbon and this bromine, I'm going to draw it this way to remind me that this is a polar bond, right? So when we draw our dipole, it looks like that, right? Got that little arrow going this way. So the electrons within this bond are moving towards the bromine. All right. So that makes that slightly positive, and this is slightly negative, right? That slightly positive carbon happening here. Okay. So with this one, this oxygen, this has got a full negative charge. It's not a partial negative. It's a proper negative. So that's a strong negative charge. It's going to be attracted to that carbon right there. So the electrons are attracted. I cannot spell. You know what's going on in my head? Attack and attract are blending together to form attract. But maybe that'll work. I don't know. Are attracted to that partial positive. Here, I'll even write it in blue. We'll write it in blue. There we go. So they often call this an attack. This is called an attack. So what's happening is this nucleophile is attacking this slightly positive carbon. And it's doing that through the electrons. So the electrons move, and that's what the arrows show. So when you're looking at a mechanism of a reaction, you're looking at the electrons around a particular atom, in this case, it's oxygen. It's attacking this carbon here, and it can do that because you got this super electronegative bromine just hanging out, and it's pulling all these electrons this way. So that makes room for oxygen to be able to swing right in, attach right there, and then that bromine kicks off and goes with the rest. So that's what this one represents. Bromine's like, I've got them all on my side of the bond anyway. It doesn't take much just to go ahead and kick off bromine. So the electrons in the bond leave with bromine. So these electrons that were shared between this carbon and bromine have now joined bromine. Bromine can leave, and oxygen can fill in those electrons that bromine took. How are y'all doing with that? You got to tell a story sometimes. I find that if you come up with a story, I often call oxygen sexy oxygen because it wants to hook up with everything. Oxygen will steal your girl. Come right in. Okay. Well, this happens all at the same time. It's so fast. When you have something like this, and you've got a bond where bromine almost has all the electrons anyway, all you really got to do is just nudge it a bit and it falls right off. So as this attaches, this one leaves. Think of it like carbon's hooking up with bromine, oxygen comes home, and bromine goes out the back door really fast. So it's like, you think of a movie or something. That's how I remember it, but maybe you don't want to remember it that way. And that's okay. It works. So it happens at the same time. It's like a comedy. This comes in, and this one buggers off. So when you see the arrows, that means that's where the electrons are going to. So we've got to keep tabs on where the electrons are going. And that's why they move that way. This one, bonk. Now, the cool thing about this is you can build all kinds of different structures with ether reactions. So if you have an alkoxide that looks like this, if you're wanting to bring in a little piece of a structure that's shaped like this, you can have your nucleophile right there and you end up with a structure like this. Same thing here, but in this case, we've got the bromine here. We've got our alkane here. We can connect through these two different ways. It's kind of neat. So this seems to be the preferred path for the two. So let's think about why. Why would this be the preferred path over this? Yes. So also this oxygen, it's got these three carbons. Do what? This one is more stable if you remove the bromine. This one is less stable if you remove the bromine. So what that means, remember, if I pull off this bromine, this carbon's going to have a slightly positive charge. It's got two other carbons to help it cope. This is going to take longer. This one is going to happen a lot faster because once this bromine goes, this carbon doesn't have anything to help it maintain that positive charge. So it needs something to bond with immediately. Remember, we get by with a little help from our friends. Whatever you're doing to a carbon, if it has a lot of friends around it, it's going to be more stable than if it doesn't. So anything that is less stable with a positive charged carbon, it's going to want to grab a nucleophile faster. That may take a minute. That's okay. So that's what we call Williamson ether synthesis. Williamson ether synthesis. Fancy word for this person figured out how we make ethers. We can do it this way. These are the two ways usually. This one's faster because of carbon cation stability. Okay, so how do we make an alkoxide nucleophile? Well, we got to pull a hydrogen off. So it can start out as an acid or even with an alcohol group. So if you remember, with acid-base chemistry, the majority of reactions that happen in living systems are done with acid-base chemistry. Do y'all have any questions? No? That's okay. Woo. Okay. So all right, so when we're making alkoxides, so that's an alkane with a negatively charged oxygen, right? Making alkoxides, an alkane with a negatively charged oxygen. We tend to start out with an acid of some sort. This hydrogen is an acidic hydrogen. This hydrogen is an acidic hydrogen. So that means it can easily leave, right? So this hydrogen can pop right off and pop back on again. So when it does that, when this hydrogen pops off, the electrons stay with that oxygen. So here, one of these electrons technically belongs to hydrogen. That's how a covalent bond works, right? They're sharing. But this hydrogen's going to let these electrons go with the oxygen. And this hydrogen can pop right off into a positively charged ion. Now, if you have something like this floating around, you've got NaH, sodium with a hydrogen on it. Let's see. Hydrogen can have a negative charge. It's not going to be very happy with that. But since these two, this one, let's see how they have it over here. They've got hydrogen with both of these. We'll put it on this side. Okay. So hydrogen's retaining ownership of both of the electrons in this relationship. And this is going to attack this hydrogen on the oxygen. Because remember, this is a polar bond, right? This is a polar bond. The electrons were already kind of leaning over to that oxygen. And since this is a polar bond, that hydrogen is going to be slightly positive. This other hydrogen that's full on negative is going to pick up that hydrogen. And then we're left with that alkoxide. With that full negative charge. Now we can take that and move on to making an ether, attach it to something else, or swap it out with one of the SN2 reactions. How are y'all doing with this? Doing a little bit better? Nah. I'm not going to worry too much about epoxides. Just know what they are. Let's see. Here, we're looking at hydroxide as a leaving group. We don't really see OH itself as a leaving group so much with a nucleophilic substitution because it can get a bit complicated. That hydrogen is more likely to pop off than this whole thing. This prefers to stay on the carbon. It's not a good leaving group. So between the two, we're going to see more halogens are the ones that we tend to see swapping stuff out. It's less complicated. They happily take all the electrons in that bond. Oxygen, it's a bit more complicated. An oxygen carbon bond is really stable compared to like a carbon halogen bond. So it's harder to break those up. They don't break up as easily. Okay. So let's look at elimination and substitution reactions of alcohols. So we've talked about how we make alcohols and ethers. We've focused a lot on ethers. Let's look at how we do alcohols. Okay, do y'all remember pKa? We need a review on that. Okay, that's all right. Let me erase right here. pKa. So this is what it means. The negative log of the acid dissociation constant. Okay. Now what this means is how well an acid completely separates. So, an example, strong acids completely come apart. So hydrochloric acid will always separate into this. It does not go back together. It doesn't come back together. It does not come back together. Now, if we're talking about a weak acid, trying to remember the formula of acetic acid, I'll just draw out something like this. This would be an example of a weak acid. Carboxylic acid, it goes back and forth. So it'll separate into this, and it'll come back together. Weak acids do not completely separate. They come back together. They go back and forth between these states. So, how well an acid completely separates, we give that a particular number. So that Ka, that essentially is this. Acid apart, amount of acid apart, divided by the amount of acid together, right? So we take how much of this there is in our solution, that number, it goes here. And we take how much of this we have in the solution, and that number goes up here. So if we have a whole lot of stuff that's apart and just very little that's together, that's a big Ka, right? If this number's big and this one's small, that's a big Ka. If this number's big and this one is small, that's a small Ka. So when we take the negative log of a big number, we get a small number. When we take the negative log of a small number, we get a big number. So it's kind of like pH. The more acidic something is, the lower the number. So once we do that negative log, that's what that P means. If this number's huge, it's going to be a smaller number once we take the negative log of it. So for pKa, pKa of this group, this R-OH plus a strong acid, see, ROH2 plus. This is a strong acid. Okay, so this protonation, let's see, of alcohols only occurs with very strong acids. So this is a weak base. Once that hydrogen pops onto there, if something's a weak base, what does that mean in its acid form? It would be a strong acid. If something's a weak base, then it would be a strong acid. This chlorine, since this completely separates, Would it be really good at taking this hydrogen back? No, because it doesn't come back together. And since it doesn't come back together, this is a weak base. But in its other version, it's a strong acid. So once I put a hydrogen on there, it's a strong acid. It's a weak base without it. So the only way I can make this OH group really good as a good leaving group is to force another hydrogen on it through a strong acid. Now, once I do that, this whole group can leave. This whole group can leave this carbon chain. This is essentially water, right? H2O. So if we take an alcohol, drop it, it could have a long carbon chain on the side, drop some strong acid in there. It's going to add a hydrogen to this. Then we essentially have a water molecule right here. It's going to be real easy to pull that right off and put something else in its place. So, something has a pKa of -2. What does that tell you about the strength of its acid? Strong, very strong. Right, so this is a good leaving group because it'll be happy to leave electrons in that particular group. Okay, let's look at, okay, ethers are poor leaving groups. Yeah, I mean, you can do stuff with ethers, but this isn't going to leave. You can just break them open by throwing in, you can break open epoxides by throwing in a nucleophile, but okay. Let's look at dehydration reactions. Okay. Y'all doing all right? So far, we've talked about S and so we've talked about substitution and elimination reactions. It's a good leaving group. OR is not a good leaving group. Now let's talk about dehydrations. This is another type of elimination reaction. Okay, I'm going to go over to that board. When you're dehydrated, what are you losing? Water. Fluids, mostly water. The other stuff's in it, right? So when we do a dehydration reaction, we're losing a water molecule every single time. And when we do that, we can form an alkene. So if we've got something like this, are these two carbons right here within that straight bond? Are they primary, secondary, or tertiary carbons? Tertiary, that's right. Yep. I'm probably drawing these weird. Fine. All right. Doesn't matter. These can spin. So on this one, let's see. We got a carbon. So these are secondary. Sorry. We got the 3 lines. I fell for it too. This has got a carbon here. So these are both secondary because this is an oxygen, not a carbon. And that's a hydrogen, not a carbon. So they're secondary carbons because they only have 2 carbons attached to them. Oh, wait, yeah, and then they do have another one connected. Y'all are right, because this one's connected to that one too. Okay, so No. So these are tertiary. I messed up because this carbon is attached to that carbon and it's attached to these two carbons. Yes. So I was wrong. I messed up on that one. All right. So we have a tertiary carbon and a tertiary carbon. And since these are tertiary carbons, they are okay to lose stuff because they have carbons around them, right? So this is a tertiary carbon and this is a tertiary carbon. Got that carbon attached to it, this one and this one. I probably made this line too big. That's all right. Carbon here, got those attached to it as well. So let's see what's going on. This is probably shorter than what I drew. So if we've got hydrogen on this particular carbon and this hydroxyl group on this particular carbon, these two can interact with one another and leave, and then we can form a double bond. Let me see if they've got the arrows drawn out. Okay. Ooh, we'll come back to that in a second. All righty. There's different ways, okay, that we can do this. All right. So when we have something like this, if we add a strong acid, we can just pop this right off. We got plenty of hydrogens here. We got a hydroxyl group here. These two can come together, form water, and then that's going to form this double bond. So we have this plus a strong acid. That strong acid is going to cause these two to interact with each other. So if I've got these electrons on the outside of this oxygen, I already have some movement of electrons moving towards that oxygen anyway, because if you remember, that's slightly positive, slightly negative. And then here, when we've got a strong acid around, if we do HCl, it's going to look like this, right? It's going to completely separate. Then we can protonate this hydroxyl group. So these are going to be attracted to this and make little water molecules. You end up with H2O. You're also going to run into situations where these can also, hold on, be attracted to that hydrogen. They can also be attracted to that hydrogen. Because this hydrogen, because you've got oxygen involved, all the electrons are kind of moving this way anyway. This hydrogen might actually feel a bit of that pull from the oxygen. You can have connection between here. So let me make a note. This oxygen is attracted to the hydrogens in the strong acid and the hydrogen attached to that R group. I'll write it this way. That hydrogen that's attached to that R group. So when that pops off, we end up with an alkene. When these two leave, these carbons are now stressed out. They're going to form a bond with one another. So when H and OH leave the molecule, carbons are stressed out because one took all the electrons and one left the electrons. So in this situation, oxygen takes all the electrons. And because this carbon is a tertiary carbon, that positive charge is going to be shared. The stress of that charge is going to be shared. So this hydrogen can pop right off. Then these two can form a double bond. Yeah, it's like a whole story. You know, maybe we should do a soap opera around carbon and its many, many issues. The short, well, I say short time, the year and a half I went to nursing school, at lunchtime around 11, we all had to go downstairs and somebody be turning on The Young and the Restless. Oh, no, it probably hasn't. All right. So I can't do that again, man. I can't fall down that rabbit hole. But, you know, maybe you could write a story about carbon and how it gets stressed out because oxygen keeps stealing the electrons. Or every time it hooks up with oxygen, you know, prone to dehydration. Maybe. Yeah, so if we take a group that has an alcohol, there's like a nearby hydrogen. This can come together and form water in the presence of a strong acid. Yes. And form a double bond. So let's write this in words. So here, increasing rate of dehydration. This primary alcohols less likely to engage in dehydration reactions than tertiary. All right. Let's write down what we know about dehydration. Dehydration reactions with alcohols. Okay. That's an elimination reaction. Hydrogen becomes H2O, right? Elimination reaction. These two leave our molecule, right? Use strong acids to get it to happen. So acids with low pKa's and low pHs, right? And when this happens, it forms alkenes, you know, carbon, double bonded carbon. If we pull something off a carbon, pull it off of two carbons, they're going to bond with one another. Okay. Any questions on this stuff so far? Well, hopefully the sound is fine on the video. All right. Tertiary alcohols are the fastest. So we could even write that down if we want to remind us. Hydrogen and hydroxide leave our molecule of interest. So we pull off a hydroxide, pull off a hydrogen. Yep. And then we've got, tertiary alcohols, strongest, well, not strongest, fastest. We'll say fastest. Fastest. Primary alcohols, slowest. Right? This is going to require more taken energy and stuff. This tertiary doesn't, it's more reactive because of all the other carbons. Okay. So here we've got Zatzev's rule. Okay. So all this is stating is that the more substituents, the more substituents that you have with an alkane, well, with your starting carbon, the more carbons you have that are attached to the carbon with the alcohol, the more the more constitutional isomers you're going to have with a particular reaction. So let me put that in other words. All right. I'll come over here. So what that means is if you've got tertiary alcohols, so here I've got a carbon here, and a carbon here, just attached to this one. This is my main carbon because it's attached to that alcohol group. These other carbons are just not my main carbon. Since I have all of these here, I have lots of different ways that I can form a double bond. So the more carbons you have, the more carbons you can stress out, the different versions of double bonds you can have. That's what Zatzev's rule is. Let's write that in words. I'm going to go over here. So we put that in words. The more carbons attached to your primary carbon. Oh, no, not to say primary. That's wrong. We're not going to do that. We're going to get confused. The more carbons attached to your main carbon, let's attach that OH. So it looks like this, maybe this. Your main carbon, the more carbons you have around it, the more versions of double bonds you're going to have. So isomers. If I stress out this one carbon, and it relies on the other carbons to help it out, I can form a double bond here, I can form a double bond here, and I can also form a double bond here. So any one of those R groups, any one of those carbons can take on the burden with that stressed out one. Like in this example. I've got this carbon here. It's going to be the one that's stressed out. It's feeling the pull of the electrons with this oxygen. So when I add a strong acid, this is going to be the thing that pulls away. And this is also capable of taking a nearby hydrogen off of this carbon and a nearby hydrogen off of this carbon. So as this is pulling on this carbon here, it can pull also on one of these hydrogens or one of these hydrogens, which means I can form a double bond here, and I can also form a double bond here. Hey, yeah, we still in class. Now, let me finish, man. Yes. It's okay. If you're ever confused, look at my door. My schedule is there. All right. These two carbons are kind of similar. No. These two carbons are kind of similar because they're both carbons with 3 hydrogens on them, right? So any one of these, you could pop a hydrogen off of that one. You could pop a hydrogen off of this one. So these are our 2 main structures that we get. We would expect to find this one more often than this one, though. Why? Why would we find this one more often than this one? What's the difference between the 2? Look at those beta carbons. This one's attached to another one. Yeah, they're on this, like this is on this side and this one's on this side, but this one has another carbon attached to it, doesn't it? This one doesn't. That's okay. We're introducing them now. That's okay. Okay, so the reason why this is considered the alpha carbon is because it's got the functional group attached to it. Others are just carbons on the outside of the one that we're interested in. Yeah. Yep. Yep. Yeah, main carbon. So
it's branched, which tells me that there's a carbon in the middle, and for some odd reason I want to think that they're
so this carbon's attached to all of these. This one is only attached to this carbon, though. Yeah. So this carbon's only attached, is the only one that's attached to this oxygen. Now, if this carbon was attached to this oxygen, then that would be the important one, right? Yep. They're going to be the ones that this one stresses out. It's stressed out. This one or one of these 2 are going to have to compensate. Same amount of carbons here. 1, 2, 3, 4, 5. So I've got 1, 2, 3, 4, 5 here. 1, 2, 3. No, but there's 4 electrons in it, though. Mm-hmm. Yep. No. But, there's 2 carbons here, and they've got 4 electrons shared between them. No, 4 electrons. It's okay. All right. Let's look at the different mechanisms. We can do E1 or E2 in our elimination mechanisms. It's okay. So our E1 Our E1 mechanisms, when we're going back to our little chart here, let me get here's my markers. When do we see E1 or E2? So, secondary and tertiary alcohols, we do E1. Primary alcohols, E2. If we want to make a note on here, you can also put secondary alcohols or middle speed, right? But they also undergo E1. So if you see a carbon like this here, an alcohol, let's see, 1, 2, 3, 4. So this is butanol. There's 4 carbons, butanol. This one, we've got the way that it's set up, it's a tertiary alcohol. The carbon that is attached to this OH is right here. So that's our main carbon. And here's our beta carbons around it, our just extra carbons that all are attached to the main carbon. So this one, we put in a strong acid. We put in a strong acid. This oxygen takes all the electrons in this bond. That's what the arrows are showing us. The oxygen takes all the electrons in that bond. This oxygen's electrons are attracted to this hydrogen, pops onto here. Now we've got a water molecule attached to our carbon. It's going to hop right off, right? We've still got extra hydrogens happening right here. So this one can come in, hop on, take the place here. We add this. This hydrogen comes along here. This oxygen leaves, form our carbocation. Double bond shows between these two. So let's write this out in words. Okay. Now, people think that one common misconception is that once the hydrogen on an acid reacts, you don't have more hydrogens left. And that's not true. We don't technically have just one acid molecule in here. We have a lot of acid molecules. So this hydrogen can pop onto here off of an acid molecule. All right. We still have acid molecules floating around. So this hydrogen then can pop onto here from this. Still got more acid molecules floating around. Now this one is a base. Now it's lost one of the hydrogens. We started out with this hydrogen, this one, that one lost. This one pops off in the presence of that one where it's negative. Then we have another hydrogen hop onto here. Oh, wait, no, that comes off of there. Okay, and this one pops off of here and forms double bond. Let me put this in words better than that. Okay. So for our E1 mechanism, it's 2 steps. It's multiple steps. Multiple steps. Okay? So with the E1, it's multiple steps. First thing that happens, the OH is attracted to the acidic hydrogen on the strong acid. right? The OH is attracted to the acidic hydrogen on the strong acid because before it leaves, it's got that partial negative charge. So let me make it a bit more accurate. There we go. Okay. Hydrogen, second thing that happens, hydrogen, the acidic hydrogen, attaches to that OH that's on the molecule, attaches to the so that's got that partial negative charge, and it forms HOH R, right? Now I've essentially got H2O going on here, right? So now it's positively charged. Third thing that happens, that positive OH2, this leaves the molecule. This OH2 leaves the molecule, and carbon keeps the positive charge. And that's what's happening here. Carbon keeps that positive charge. All right. The next thing, a hydrogen on a nearby carbon leaves electrons in the bond and pops off. Pops off. And it ends up joining with the negative. I'm trying to tell a story so you can at least put this with the picture, right? Yes. Then it forms a water molecule attached to the carbon, right? So this water molecule pops off, but it leaves that positive charge behind on that carbon. Yeah, so you have anions that are floating around in your water from your strong acid, right? Hydrogen can be attracted to it, right? So you got a hydrogen on a nearby carbon. It leaves. Now those two carbons can form a bond together. An alkene. So nearby carbon and positive charge carbon form a double bond. It's a lot. Here's fewer steps, but you may not. Yeah, the heterolysis of the CO bond forms a carbocation in the rate determining step. Huh? Yeah, it's in your notes too, in the module. It's fine. Either one, you can still take a picture. So this is the E1 mechanism. It's multi-steps. Maybe that's slower. Certain ones are fast. So whatever the slowest step is, that's going to be the determination of how fast the reaction is. I may have mixed these up. That's okay. Let's put this in terms of stability. That should still be middle speed, I'm thinking. Okay, let's look at this in terms of stability. That should probably be the slowest. I don't know. Okay, most stable, least stable. All right, that would be a better descriptor. Because since this is multiple steps, it may not always be true that it's faster. So, okay. So that's E1. Okay. Now, Thursday, we'll talk about E2. It's not multiple steps with E2. It's usually just, well, it is, but it's different. E2 mechanisms. We'll get into that. So in your homework, I guess work on the next part for that. We've got the PowerPoints are in the modules. That's chapter 9. Your homework is here. Yeah, just put most stable and least stable because I think it's one of those relative things. It's relative. All right, so the first chapter, 9, with these, we already talked about naming and positions, primary, secondary alcohols. Remember, you don't have to do all of these to turn them in. Yeah, so this one is naming. So I've got to fix that. Okay. So these are all, this is all naming stuff. So where we should be in the homework, let me see what, okay, so we're at synthesis now. So you should have like 4 or 5 questions done through question 22, because that's what we covered last time. So we should be up through here. Now we've started getting into synthesis. That starts at 23. Now remember, we haven't gotten to all of these synthesis. Yeah. So we're at synthesis. So start paying attention to whether something would be a substitution or an elimination. Now here I'm thinking probably dehydration. So when you're looking at this, start paying attention to where the electrons are going. When does this stop? So this is probably the rest of it. We're talking about carbocation rearrangements. So up through 23 through 29, that's about 6. You only really need to turn in about 2 of these because there's a lot of repeating of the same types of problems. You only got to turn in 1 version of that to me. The extras are there just for practice. Okay? Yes. It's up to you. It probably would be helpful to know which problem it is, though. So I don't have to go hunting. Yep. You got it.